Thank you for visiting our presentation. In this work, we will present a robot vision system which uses sensor tilting and mirrors to diminish occlusions in the scene. Occlusions stand as a large challenge in robot vision systems because with occlusions, there is a danger of overlooking or even damaging the target. And as a rule of thumb, occlusions in the scene can be minimized by placing depth sensors on the zenith of the robot workplace, which many commercial robot systems follow. However, even with careful arrangements, as shown, occlusion is always created directly below the robot arms, hiding objects underneath. Even in such a simple setup, the effect of occlusions are significant, that a single box can be mistakenly recognized as multiple boxes. So, we can also tell that such occlusions become even more challenging when multiple robots work together in the same environment. There are two main approaches to reduce occlusions in robot vision systems. In principle, the only way to reduce occlusions are to increase the number of camera viewpoints. One is to install multiple sensors in the workplace. While this is a straightforward approach, it can effectively reduce occlusions without affecting the robot work efficiency. The only shortcomings is the increase of the sensor cost. We can also install multiple sensors. We can also install sensors in the robot's end effector and reduce occlusions by manipulating the robot so it would sense from multiple viewpoints. This work senses from 15 predefined viewpoints per scene. Although this can reduce the sensor cost, the robot work efficiency is harmed since it must sense from multiple viewpoints before even manipulating the object. So, to summarize, the conventional methods has a trade-off between work efficiency and sensor cost. We propose the first robotic vision system that can adaptively remove occlusions utilizing mirror reflection and sensor tilting. The basic principle is simple. We first perform the basic sensing from the zenith sensor, referred to as direct sensing. Then we perform reflection sensing by utilizing the tilt unit attached to the sensor. Tilt unit makes this sensor face to the mirror and non-line of sight sensing is done, which removes occlusions generated during the direct sensing. The objective of this research is to eliminate the occlusions created by the robot arm operating in the workplace, foreseeing future issues when multiple collaborative robots operate within the same scene. There are mainly two advantages using this method. The first is that the occlusions can be reduced by using a low-cost mirror and a tilt unit without increasing the number of expensive 3D sensors. Another advantage is that the tilt motion is a simple single-axis motion, which enables much faster sensing than robot arm-based motion by end effector sensing. The operation of our sensing system is described next, along with the signal processing pipeline. First, direct sensing is performed, as in conventional robot vision systems. However, in this example, the occlusion is caused by the robot arm itself and will cause the tomato to be missed, as seen in the point cloud as in the left. So, in this pipeline, we first detect the occlusion area from the direct sensing results. As here, the area below the robot arm is detected as an occlusion area. Then, based on the coordinates of the detected occlusion area, the optimal tilt angle that can cancel out the occlusion is calculated. Then, using the derived optimum tilt angle, the sensor is actually tilted and reflection sensing is performed. Because of this adaptive occlusion detection, and by adaptively setting the tilt angle, even if the robot arm itself or the robot arm position moves significantly, the program does not need to be modified and will automatically set the optimal tilt angle for operation. The results of the direct sensing and reflection sensing are combined after transformed into work coordinates. We can sense the area under the robot arm. As you can see, a point cloud of tomato is obtained by using both the direct sensing and reflection sensing results. Next, we describe the method for detecting occlusion area in the pipeline. While we can think of several approaches to realize this, we decided to go with the simple rule-based method using the height threshold. The height threshold is determined as the maximum height of the object that may exist in the workplace plus some margins. The centroid of the largest occlusion area is adopted to derive the tilt angle. The height threshold-based method is effective when the environment is simple, but DNN-based methods may realize more general occlusion detections. However, because the execution time of DNNs were long in our design, it consumed a significant portion of the sensing time of our system as in this equation shown. Therefore, we decided to stick with the simple rule-based approach. Next, the specific calculation of the tilt angle is described. The occlusion coordinates xt obtained earlier are transformed into the mirror image coordinates xtv using the inverse of the transformation matrix hm. Then, the tilt angle can be derived from xtv, which is shown in a simplified equation in 2 dimensions, as shown here. The key here is the transformation matrix hm, which is an important transformation matrix that is also used to convert the virtual mirror data to world coordinates. Such hm can be formulated by the Hausborder transformation if the location of the mirror is known. The specific calibration to obtain hm is also described specifically in the paper, so please refer if you are interested. Now, a typical question is how the measurement error increases with reflection sensing. Since 3D sensors errors are proportional to the working distance, in our case also, the most crucial error source was the increase in the working distance. For example, in our case, the reflection sensing's working distance is 1 over cosine c to tilt longer in this case. So, since our error in our sensor in Senso N35s was proportional to the square of the distance, so for example at c to tilt of 45 degrees, the measurement error was 2x larger than the direct sensing path. We also analyzed that error owing to the mirror reflectivity is small enough, since the mirror reflectivity is quite high, over 90% for most consumer-based mirrors. From here, we will talk about the experiments we have conducted, and this shows our experiment setups. The depth sensor is mounted on a tilt unit, which is FLIR PUTE46, and the depth sensor we used was Senso N35. The depth sensor is mounted on a tilt unit at the zenith of the workplace. An off-the-shelf mirror is placed 1.2 meter front of the robot arm for reflection sensing. We would like to note that there is nothing fancy about the mirror, and it is an ordinary mirror bought from Amazon. As described earlier, the sensor performs direct and reflection sensing in turn. This shows the direct detection results using only the direct sensing data. Due to occlusions, a single box is misinterpreted as multiple boxes. And in turn, this shows the results using both the direct and the reflection sensing data. As we can see, occlusions are greatly reduced and there are almost no misdetections. Next, we compare the results against systems using 2 sensors. An extra sensor was placed where the mirror existed and was tuned to minimize occlusions. As seen here, the results using direct plus reflection sensing are almost equal to the results of using 2 sensors. Actually, the evaluated detection accuracy was almost the same, and had only 1% difference. We also experiment the effect of adaptive sensing. We moved the robot from the initial workplace and used that and show that adaptive sensing can track the occlusion spots. So even if the robot moves around, it can still eliminate the occlusion effectively. However, if we do not use the occlusion tracking instead with fixed angles, if the robot moves around, the occlusions cannot be eliminated efficiently. We have shown that the sensor arrangements are not required even after changes in robot operation or layout. This is our conclusions. We proposed a tilt-type mirror reflection sensing robot vision system. We showed that the occlusions can be adaptively eliminated with mirror reflections and sensor tilting. And we were also able to achieve perception results close to 2 sensor setups. And for future works, we would like to extend this work to adapting to more complex environments, like using multiple robots or multiple robot arms. Since our initial work, this work was only using one single robot arm. And also, we are also very interested to extending this environment to multiple mirror setups. Thank you very much for listening.